All right, ladies and gentlemen, let's go over some simple harmonic motion. This is Unit 6. Now, we already have talked a little bit about some stuff that is similar. That is when we talked about elastic potential energy. In that unit, we talked about what the word elastic means. An elastic object is an object that's able to restore itself to its original or previous position or shape or size. All right. So when we talk about simple harmonic motion, we're going to be getting into this ability of an object to be able to restore itself. Before we get into that, let's make sure we remember what the word equilibrium is, because that's an important thing to understand. So equilibrium is going to be the natural or resting state in which or position that the object is in. So if in this picture, for example, we have a spring. When the spring is unstretched, this is its equilibrium length. This is the equilibrium position. All right. But if we stretch that ball out, it's no longer at equilibrium. And so it has a certain displacement away from its equilibrium position. And the restoring force will cause it to go back to its equilibrium position. We're gonna talk about that. So that's the idea of this word restore, is that whenever we have an elastic object, when it's displaced from equilibrium, there is going to be a restoring force within the object that seeks to restore it to its equilibrium position. All right, so we can look at this picture right here. We've got three different examples. So if we look at A, here our object is at equilibrium. All right, it's at position 0, which is typically where we define our equilibrium position. And so because it's at equilibrium, there's no need for a restoring force. It doesn't need to be restored to equilibrium. It's at equilibrium. If we look at position B, this spring has been compressed now. And so the restoring force will push on this block back towards equilibrium. And if we look at C, here we have the spring has been stretched. And so the restoring force is again going to try to pull the block back towards equilibrium. The restoring force will always be in the direction towards equilibrium. So notice the difference between B and C. In this case, the restoring force is to the right, and in this case, the restoring force is to the left. All right. In part B, the displacement was negative. So the object was displaced to the left, and the restoring force was in the opposite direction to the right. In C, the displacement was positive. The displacement was to the right, and the restoring force was in the opposite direction, back towards equilibrium, going to the left. That's important to note and to look for. All right. So before we get into this, let's define a few words. Amplitude. Now, amplitude could simply mean any kind of displacement, but when we use the word amplitude, often we're going to be referring to a maximum displacement when we have an oscillating object that's going back and forth. All right. Wavelength is going to be the distance of one complete cycle. You can also look at it as you pick two corresponding points on a wave, and it's going to be the distance between those 2 points. But you can also look at it as the amount of distance that's covered in one complete cycle. The period is the amount of time it takes for one cycle, the amount of time it takes for one wavelength to occur. Frequency is going to be the number of waves that occur per unit time. Typically, we look at every second, but we could change that if we wanted to. It's just the number of waves per unit time. Equilibrium, we already talked about. And then oscillation is just going to be a repeated motion going back and forth between two positions. And the center of that oscillation tends to be our equilibrium. All right. Now, amplitude is going to have units of meters. Wavelength will have units of meters. Period will have the unit of seconds. Frequency has the units of inverse seconds, which we call hertz. Equilibrium, because we tend to refer to equilibrium as far as its position, we often are going to refer to units for equilibrium being meters. And then oscillation is just a basic concept. It doesn't have any units associated with it. So let's look at how the restoring force affects an object. Take a look at the guitar string. It gets plucked, and what do you notice happening to the string after the person plucks it? Well, if you look at the motion of the string, it goes up and down. It looks like something's traveling through the string, and we call that a wave. That's energy that's traveling through it. However, the string itself is going up and down. It's vibrating up and down. We can call this vibration, sometimes we call it an oscillation. All right. So anytime there's a restoring force, it's going to cause an object to oscillate. Now, this oscillation will occur between the two maximum amplitudes and on either side of equilibrium. So if we look at this image right here on the left, we have a mass on a spring that's oscillating up and down. And this line right here is our equilibrium position. This is where the block would be if it wasn't moving. If it was naturally just at rest, this is where it would be. So we have a maximum displacement right up here, and we have a minimum displacement right down here. And it goes back and forth between these two maximum amplitude displacements or amplitudes, and it is always centered. These amplitudes are always at the center of these amplitudes, rather, is where our equilibrium is going to be. We can look at the same thing over here with this pendulum going back and forth. We have a maximum displacement to the left and a maximum displacement to the right. So those would be our two amplitudes, and it goes about what we would call the origin, or the very center resting point. All right. Now, whenever we talk about oscillatory motion, we're going to get cycles or a repeated pattern. And if you recall, we talked about wavelengths. Whenever an object goes through one cycle, we'll call that one wavelength. That distance is one wavelength. So it would be the distance covered from here to here, looking at the pendulum from here, back, and there. That's going to be one wavelength. Likewise, over here, we could pick any point. Let's pick right down here at the bottom. It would be the distance that's covered when it reaches this point and then comes back to this point again. So let's do a quick review. What's a motion time graph? I want you to see if you can identify what type of this graph is, what type of motion time graph this graph is, and what that slope would represent. This is going back to our first unit with kinematics. So a motion time graph tells us really anything about the motion of an object throughout time. The most common motion time graphs that we have looked at have been position time graphs, velocity time graphs, and acceleration time graphs. So this particular graph, if we look at our axes and how they've been labeled, this one is a position time graph. So that's the type of motion time graph. And if we look at a position time graph, the slope on a position time graph, in this case, will represent the velocity. Okay, well, here's my question. What would a position time graph look like for an oscillating object? That one's going to be a little bit trickier. Give it some thought, make a prediction. What do you think a position time graph would look like for an oscillating object? Well, we get something that looks like a wave. This is called a sine curve. A sine curve. It looks like this, all right? So this would track the position of the object throughout as time progresses, all right? Well, what do you think a velocity time graph would look like? All right, what do you think a velocity time graph would look like? Well, it's actually going to look very similar. We're still going to get a sine curve. Now, this sine curve is going to be a little bit different, but they look very similar. So notice if we match them up right here, look for patterns between the two. What you'll notice, one pattern I'd like to point out, is that whenever we're at our maximum displacement, whenever we're at our amplitude, 10, negative 10, 10, negative 10, 10, negative 10, look at the velocity at those points. Velocity is 0 at 10. Velocity is 0 again at negative 10. Velocity is 0 at 10. Velocity is 0 at negative 10. So we see a pattern occurring here. That's the kind of thing that you want to look for in those things. It can help you glean some information in these types of things. So I'm not sure if you're going to get hit with motion time graphs for simple harmonic motion, but I wanted you to see it just so you can have an idea of what it should look like, just in case. Now let's talk about something called Hooke's law. This is the basis of simple harmonic motion. Sometimes it's called the law of elasticity. Most commonly, you're going to hear Hooke's law. All right. Force equals K, which is the spring constant, multiplied by whatever the displacement is. Okay, so this force is a restoring force. There are two different variations of this equation. The equation on the right is what appears on your equation sheet. The equation on the left is the one that I actually prefer. If I remember correctly throughout these slides, I use both of them. Regardless of which one you use, here's the important thing to remember. What you need to remember is that the restoring force is always going to be in the opposite direction of the displacement. In this case, on the left, that's why we have the negative here. So if our displacement is to the right, that's positive, and the negative changes the direction, which tells us the restoring force is in the opposite direction. We can see this in our image down here. At a situation B, our displacement is to the left, which is negative, so we have a negative displacement multiplied by a negative, which gives us a positive. Negative times negative gives us positive, so our restoring force would be in the positive direction or to the right. Same thing for C. Our displacement is to the right, so we have a positive displacement. A positive number multiplied by negative gives us a negative number, so our restoring force will be negative. It's going to be going to the left, all right? So if you use the equation on the right, these absolute value signs tells us that it's not going to worry about direction. So you have to go in and actually assign the correct direction, all right? So in this case, if our displacement is to the right, that would give us a positive x. And so it would make us think, oh, our restoring force is going to be positive. We'll have to manually go in and assign a negative value. That you can forget that one easily. That's why I like to use the one on the left. It kind of takes care of that for me. But I'll try to use both if I remember correctly. So one thing to mention is that nothing's perfect. So springs will follow Hooke's law. And there's going to be a point. So right here we can see a pattern. It's a straight linear line. And we'll talk about this type of graph in a little bit. But there's going to be a point where it stops following Hooke's law. The spring has been stretched too much, so much that it stops obeying Hooke's law. Typically, that's when an elastic object is starting to be damaged. Sometimes that damage is occurring on a small scale, but it's going to make it more difficult for the object to remain elastic and return to its equilibrium position. All right, so let's look at a force displacement graph. Let's look at a force displacement graph. What do you think the slope of a force displacement graph is? Well, slope is rise over run. So our rise would be in our vertical, our run would be in our horizontal. Our rise is force, our run is displacement. What would force divided by displacement be? Well, that's going to bring us to Hooke's law. Force, if we take our Hooke's law equation and solve for the spring constant, the spring constant is equal to force divided by displacement. So the slope on a force displacement time graph will tell us the spring constant. Now remember, the spring constant is a measure of how elastic the material is. It helps us know how much force is required to displace an object by a certain amount. That's the basic idea of a spring constant. So take a look at our graph, this example graph right here. What would the spring constant on this graph be? Well, we got to figure out the slope. That's rise over run. Our rise would be from 0 newtons to 4 newtons. That's a rise of 4 newtons. Our run would go from 0 to 0.4. That's 0.4 meters. 4 divided by 0.4 is going to be 10 newtons per meter. That tells us that it takes, whatever object this is, it takes 10 newtons of force to displace the object by 1 meter. All right, so now we talked a little bit about, if you recall, I mentioned at the beginning how this is kind of similar to what we've already talked about with elastic potential energy. Well, the question is, what is that relationship? How does Hooke's law relate to elastic potential energy? Well, let's go back to our graph. Calculate, here's what I want you to do. I want you to pause the video, and then I want you to calculate the area under the curve. We've got this triangle shape right here. Calculate the area under the curve, and once you get that number, tell me if you can figure out what that represents. See if you can figure out what that number represents. Well, the area of a triangle is 1/2 base times height. So we take our 4 newtons and our 0.4 meters, multiply it by half, and we get 0.8. Now, what does this 0.8 represent? All right, what does this 0.8 represent? Well, it represents work. If you think about it, we have a force multiplied by displacement. Force multiplied by displacement was our original definition of work, and work changes energy. So we can look at this 0.8 as a change in energy, which means it's going to have units of joules. All right. This should hopefully make sense. We're talking about simple harmonic motion, an object that's oscillating back and forth with springs and stuff like that. So this change of energy is probably going to be a change between kinetic and elastic potential energy. That's what Hooke's law can help us understand. It helps us to understand the restoring force that's used to do work on an oscillating system and change its energy. So sometimes that restoring force will increase our elastic potential energy and decrease the kinetic energy. Sometimes that restoring force will instead decrease the elastic potential energy, which will then increase our kinetic energy. It's going to depend on the situation. There's another way we can look at it that helps us understand how this relates to elastic potential energy. So when we calculate the area under the curve, let's just use equations instead of numbers. So our base is just a displacement, which we're going to use as x, and then our rise is our force, which is in this case a restoring force, and we know that restoring force is equal to the spring constant multiplied by displacement. So if we substitute those into our base, 1/2 base times height, we get 1/2 times our base, which is displacement, multiplied by kx, which is our restoring force, which gives us 1/2 kx squared. And if you recall, 1/2 kx squared is the equation for elastic potential energy. So this helps us to get a feel for the fact that this type of graph, which we can use to help us understand the spring constant, also can help us get a feel for the elastic potential energy and the work that's going on in the system. Okay, so here's what I'd like you to do to practice with this. This will also be a practice in your graphing and plotting. So look at this set of data. I want you to take this data and I want you to create a plot of this data. Make sure that you scale it appropriately. Don't just use these numbers as your scale. That's not a scale. Scale it appropriately, consistently. Plot each one of these points and see what you can get. After you plot it, what I want you to do is you're going to try to figure out what the spring constant is from this set of data points, okay? You need to figure out what the spring constant is for this set of data points. After plotting the data points, do a best fit line and figure out the slope of that line. Now, when you do a best fit line, here's several points that you need to remember, several guidelines. One, your line, your best fit line, needs to follow the trend of the data points. If your data points looks like a sine wave, don't do a straight linear line going through that. That doesn't follow the trend of the data. All right, so your line needs to follow the trend of the data, and you need to have equal number of data points above the line as there are below the line. So if you have 3 data points above the line, you need to have 3 data points below the line. Okay, it is okay to have data points on the line. That is totally okay. You just want to make sure that however many data points are on the line, you still get the equal number of data points above and below. The other thing I'm going to point out as a guideline is your line does not have to go through the origin. Do not try to force your best fit line to go through the origin. If it happens to go through the origin, great. If it doesn't, that is okay too. So go ahead, pause the video. If you haven't already, plot the data points Do a best fit line and then determine the slope of that best fit line. All right, when I did this, this is what my plot looked like. Notice we've got 1, 2, 3, and then a fourth one that's kind of on, kind of off. All right. And then we've got this one. I didn't do the plot itself. 8. This one, it looks like there's 1, 2, 3 that are below and 1, 2, 3, 4 that are above. So this would actually not be a good, it would not be a perfect best fit line. I did have a program do this for me. It didn't do quite as good a job as I would have liked. However, I was able to get it done faster. So that's something to check for. This is not perfect, but you should have gotten somewhere around 97 newtons per meter. Okay. If you were off just by a little bit, that's okay. This best fit line is not perfect, so I'd expect your answers to probably be a little bit off of this. But if you're pretty close to the 97, we'll call that good. All right, here's another practice problem. So we have a block of mass. It's half a kilogram on a horizontal surface, and it's attached to a horizontal spring with that spring constant of 50 newtons per meter. The other end of the spring is attached to a wall. You can neglect friction throughout all of this. So when the spring is unstretched, that block is located at 0 meters. Now remember, this is going to be our equilibrium position. So the block is then pulled to 0.3 meters and it's released from rest. What is the magnitude of the acceleration of the block and the direction of the net force exerted on the block when it is located at 0.3 meters? So think about the equations we've used. Think about Hooke's law. You're going to have to really think about this, maybe relate it to some stuff we've already talked about. Pause the video, see what you can come up with, and then go ahead and listen to my explanation of it. All right. So the direction of the restoring force is always towards equilibrium. So it's pretty easy in this case. We don't have to do any calculations. If the displacement was to the right or in the positive direction, then the restoring force is going to be in the opposite direction of that. It's going to be to the left or in the negative direction when it's at the 0.3 meter position. So we got that part done. That part wasn't too bad. So we're going to look at Hooke's law, and we're also going to use Newton's second law here, all right, because it was talking about acceleration. So we want something that relates force with acceleration, and Newton's second law does a very good job of that. So in this case, our restoring force is going to cause the block to accelerate. As such, we can set these two equal to each other. We can set them equal to each other. When we do this, we can solve for our acceleration. When we get this, and then when we put our known values in, we can calculate what the acceleration actually is. All right? Plug in your numbers, you're going to get 30 meters per second squared. Now, I have made a mistake in this. See if you can figure out where my mistake is. There's one thing that's not quite right with this. Well, if we go back to the previous one, you'll note I didn't assign a direction. We already said that the restoring force is negative. So technically, that was a horrible negative sign. That should have been negative kx. All right? Should have been negative kx. So going back to this equation, technically our acceleration should be negative. The acceleration is in the same direction as the force, and we know that the restoring force is to the left or in the negative direction. Therefore, our acceleration should also be negative. So technically, the answer should be negative 30 meters per second squared. All right. Take a look. Got a bungee jumper. Okay. I want you to tell me at which point during the fall is the bungee jumper going the fastest? At which point during the fall is the bungee jumper going the fastest? Well, Right after the bungee jumper jumps, they're going to accelerate faster and faster and faster until that restoring force from the cord starts to act on the jumper. Once that restoring force starts to act on the jumper, the acceleration will be in the opposite direction that the jumper is traveling, and it's going to cause the jumper to slow down. So that one moment when the bungee cord is fully extended, but it hasn't stretched yet, that's going to be the moment that the bungee jumper is going the fastest. So if we look at this little image right here, faster, 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 stop. Right when that restoring force kicks in, that one moment, that's when the jumper is going the fastest. All right, let's see if we can think of some examples of an oscillating motion. There's quite a few examples that you could probably find in the world. We're going to focus in on two specific ones: a mass on a spring and a pendulum. So let's look at a mass on a spring. So you're going to want to make sure you understand what amplitude is, what period is, and what frequency is. So maybe go back earlier in the video, look at that, look stuff up online if you're a little unsure. Just make sure you understand what those words mean, okay? Now, period and frequency do have an influence on each other. Just to make a note of this real quick, the period is equal to 1 over the frequency. This type of relationship we call inversely proportional. If our frequency increases because it's in the denominator, that means our period will decrease. All right? So let's take a look here. What factors do you think are going to have the biggest influence on the period of this mass on a spring? So keep in mind, remember, period is the amount of time it takes for one complete cycle to occur. So we would start timing here, and we could stop timing here. That would be one cycle, so that would be what the period. All right. What do you think has the biggest influence on a mass on a spring, on the period for a mass on a spring? Well, obviously the mass is going to have an influence. Bigger the mass will influence, smaller mass will be different. And also the stiffness of the spring, or the spring constant. Does this have a very high spring constant, a very low spring constant? If we look at our equation, we can understand exactly how much. As we increase our mass, if we put a bigger and heavier object on this spring, the period's going to get larger and larger and larger. However, with the spring constant, if we increase our spring constant, make it more and more stiff, that's going to decrease our period. If we want to increase the period, we need a spring with a lower spring constant. Okay, so M stands for the mass on the spring. K stands for the spring constant of the spring itself. And this equation will tell us the actual period for a mass on a spring. So let's practice. When a 0.05 kilogram mass is attached to a vertical spring, it is observed that the spring stretches 0.03 meters. The system is then placed horizontally on a frictionless surface and set into simple harmonic motion. I want you to tell me what is the period of the oscillation. All right. Now, as a hint, you're going to have to use Newton's second law and Hooke's law here to help you with this problem. Okay. All right. So before we can figure out the period, we got to know what the mass is in the spring constant. Okay. We don't know the spring constant, so we're going to have to use another equation to figure it out. That's where Newton's second law is going to come in. Now, as we put the mass on the spring and let go, it pulls down on that spring, and the restoring force is going to start to accelerate that mass. So here we have this. We have our Newton's second law applied to this situation. There's only one force in this case, and it's the force of gravity. All right. And that force of gravity is going to be equal in size to our restoring force. Since our displacement is down and negative, that means the restoring force is going to be positive. So this is how it ends up looking. All right. We can solve for our spring constant in this situation. Once we know that spring constant, we can actually substitute it into our period equation. So we take this spring constant equation we just figured out, and we substitute it into our equation. We get this equation down here on the bottom left. Well, we can always multiply. When we have are dividing by a fraction, it's the same as multiplying by the reciprocal of it. So we flip this around, multiply, and you get mx divided by mg. Notice those masses are the same, so they can cancel each other out. All right. Once you input your numbers, you're going to get a period of 0.344 seconds. All right. If you use 9.8 meters per second squared, you're going to get 0.348 seconds, right around there. All right. Sometimes the system doesn't look quite as nice as we would like, and you have multiple springs acting or in our system, set up in a variety of different ways. So rather than trying to treat this as two different springs, sometimes what we can do is we can pretend that there's one spring that has the same effect as these two springs working together. All right. Let me see if I can think of an example. That would be like saying, okay, you have two people that can lift 50 pounds each. So they both can lift 50 pounds, but instead of having two people that lift 50 pounds each, instead, we could say that we have one person that lifts 100 pounds, and they can do the same thing as the two people working together. Kind of a similar idea here. We've got two springs that are going to be working together. To make our life simpler, if we can just imagine a single spring with a different spring constant that operates and works the same way, that's going to make our life easier. That's what we call our effective spring constant. All right. Now, the effective spring constant will depend on how it's set up. When you have multiple springs set up parallel to each other, you can have 2, 3, 4, 5. All you're going to do is add up all of those spring constants together, okay? So in this case, we have two springs, so our effective spring constant is going to be the spring constant 1 plus spring constant 2. If we had 5 springs, we would have spring constant 1 plus spring constant 2 plus spring constant 3 plus spring constant 4 plus spring constant 5, all right? So this is in parallel. Notice each spring is not connected to each other. Each spring is connected to the wall or whatever else, and it's connected to the mass itself. They aren't connected to each other, all right? The next one is going to be in series. They are placed one after the other. Notice, only one spring is connected to the mass. The springs are connected to each other. This is your basic equation right here. And again, for each spring with a spring constant, you're just going to add more and more terms. So the inverse of our effective spring constant is equal to the inverse of the first spring constant plus the inverse of the second spring constant plus however many spring constants there are. So for this situation, with just two springs set up like this, if you solve for your effective spring constant, this is what your effective spring constant will look like. Because you got to remember, this equation that we start with is not the effective spring constant. It's the inverse of the effective spring constant. To figure out the effective spring constant, you have to solve for it, all right? So in this situation, with these two springs set up exactly like this, this is what it's going to end up looking like, all right? So a mass M is attached to two springs with force constants. Or sometimes they're called force constants. I like to call them spring constants. K1 and K2 respectively. K1, K2. The mass can slide horizontally over a frictionless surface. So it's arranged as we show, not above but below. What is the period of oscillation for this situation? You're only allowed to have these three variables plus fundamental constants in your answer. So go ahead, pause the video, see if you can come up with an algebraic solution. All right. So to start, actually, I don't really show you now that I think about it. Okay. Either way, this is what your answer should be. I forgot that to try and save on time, I went ahead and just calculated. Go ahead. Hopefully this is what you got. The first thing, I will tell you, the first thing you have to do is figure out what the spring constant is, the effective spring constant, and then you substitute that into your period equation. If you have questions on that, you can just let me know and I'll help you out. So we're going to take a quick little side tour for a mass on a spring. I want you to see if you can figure out what is the maximum energy. We're going to go back to our elastic potential energy. What is the maximum energy for a mass on a spring when it's been stretched to a maximum displacement of A? That being our amplitude. And secondly, what is the energy of a mass on a spring when the mass is somewhere in between equilibrium and maximum displacement? I ask these questions because I wouldn't be surprised if you saw an AP question on the test that asked you to relate energy to simple harmonic motion like this. Well, at maximum displacement, 100% of our energy is elastic potential energy. So instead of using an X in our equation, we just replace that with an A. Now, if it's between equilibrium and maximum displacement, it's part elastic potential energy, and it's also part kinetic energy. So our total energy equals the sum of these two energies. Okay? Now, you're going to use these two answers, and what I want you to do is try to derive an equation for the velocity at any given point. If you do that, you're going to get this equation right here. This equation can be a useful equation if you need to figure out the velocity of a mass that's oscillating on a spring at different locations during its oscillation. All you have to remember is A is that maximum displacement. It's the amplitude. And then X is wherever it's currently at. This is going to help us know the velocity. Now notice this is a plus or minus. You'll just have to assign the appropriate direction depending on where it's located. All right, one of the last things we need to talk about for simple harmonic motion is a pendulum. All right, so I want you to practice real quick. See if you can calculate, I think I said frequency here. What I'd like you to do is instead of frequency, go ahead and do period. I'll correct that in the slides. Go ahead and see if you can calculate the period of this pendulum. Well, there's two things we could do. One, we could time it. Now, because this is happening pretty quick, rather than trying to time one period, one cycle, that would be starting from here and then stop. That's pretty quick, and people make mistakes that way. One of the things I like to do is I will measure it for 10 cycles, and then I divide that total time by the number 10, which will give me the average time for one cycle, and the time for one cycle is period. So I would start timing, let it oscillate back and forth 10 times, and then I would stop timing it, and I would take that total number and divide it by 10. Or if you happen to be looking at this graph, you can see that it goes one complete cycle and starts to repeat itself. So our period should be right around 2 seconds. And we can look at our horizontal axis to figure out that it should be just over 2 seconds. All right, so when we're talking about a pendulum, what do you think is going to have a big influence on the period of that pendulum? Well, first, surprisingly, the mass that's on the pendulum has nothing to do with the period. First, the length of the pendulum. How long is that string or arm that's a part of the pendulum? That's going to have a big influence. And then also, how strong is the gravitational field? How strong is the acceleration due to gravity? That's going to have an influence as well. Here's our equation. It looks very similar to the equation for a mass on a spring. So just note that instead of Instead of mass and displacement, we have length of pendulum and the gravitational field. So the longer the length of the pendulum, the longer the period's going to be. In the gravitational field, however, the stronger the gravitational field, the smaller the pendulum, the period of the pendulum will be. So here's what I'd like you to try and figure out. A pendulum is set into motion on the moon. The period of oscillation for the pendulum is 2 seconds. Since the acceleration due to gravity on the moon is 1.63 meters per second squared, determine what the length of the string is for the pendulum that was set up on the moon. All right. So pause the video, see if you can figure that out. All right. you should have gotten 0.165 meters. 0.165 meters. All right, ladies and gentlemen, that about wraps it up. So hopefully that wasn't too bad. If you got questions, go ahead and let me know.